So today we're going to take a look at a thing called polynomial functions and rational functions, okay? Now, when you hear the term of a polynomial function, it's a polynomial function, y is equal to f of x, is a function of the form this. A(n) x to the exponent n plus a(n) minus 1 x to the n minus 1 plus all the way down to a2 x to the 2 plus a1 x to the 1 plus a0. So it's just a polynomial of some power where basically each of the terms, their coefficients, most of them aren't 0. The only one that isn't 0 is the first one. And when I'm talking about the coefficients, we're talking about the coefficients an, an minus 1, an minus 2, all the way down to a of 2, a of 1, and a naught are real numbers like decimals, square roots, all those things. So when I say real, I'm talking about the real numbers, right? And the n value is non-negative. So here are some examples of some polynomials. These ones are all considered polynomials. And now here are some examples that aren't. So for example, these ones here, anything with a radical sign, like the first one, y is equal to 2 root of x plus 8 is not a polynomial. Okay, anything with a fractional exponent, like this one here, right? Fractional exponents are bad, are not polynomial either. And negative exponents are not polynomial. So if you have any of those things in a problem, these are not polynomials. So now let's get into the meat and potatoes of all this stuff. We have to identify some ideas. And since I don't know where you were taught, I'm going to make sure that everyone has the same terminology. So you'll notice how I kind of interchange between y equals and fx equals. To me, they are the same thing. One just tells me what the x value is, not just the y. So let's say we have this problem. Fx is equal to 3x to the exponent 5 minus 4x cubed plus 8. Now, if you have an equation like this, there's going to be 3 ideas that I want you to focus on. We have a thing called the leading exponent. The leading exponent is the exponent on the highest power. The highest powered term that is here. We call this the lead exponent. This here we call the number that sits in front of the term is called the leading coefficient. This last term here, we're going to call it the constant term. And when you're in college or university, you're going to hear people use this constantly. When you do calculus, you're going to hear your teacher discuss this as well. So it's best you learn it now. Now, you've heard of this before. When you were working with quadratics, your teachers taught you about a thing called the degree. The degree represents the highest power that you see in your list of exponents that are in your polynomial. Now, here are some examples. You've seen them before. So you've seen n0, where fx is equal to a number, right? We call this the constant function. For n equals 1, you have something that looks like this. Fx is equal to a1x plus a0. You know this as a linear function. And next, when n is equal to 2, we have fx is equal to, well, a2x to the 2 plus a1x plus a0. You used to call this quadratics, otherwise known as a parabola. So now let's go on to the things you don't know about. So for this next one, we call it a cubic. For this next one, we start with a constant and then something x to the fourth, and we call that a quartic. And we literally could just have x to the 4 and nothing, and that would still be considered a quartic. So you look for the highest power, and that identifies each of these things. So the last type of term that you're going to see is a thing called a quintic function, and it looks like. And this last one starts with an exponent of x to the 5 on its term, and we call that a quintic function. So here are some examples of some functions that you're going to have to get used to. For our line, we have something like this. For x cubed, our graph starts on the bottom and swipes up. And you should notice that it has an S curve to it. It kind of swoops, goes flat, and then goes up. Think of it as two half parabolas where one half is opening up and one half is opening down in the other quadrant. When we have something that looks like a squared, we have something like this, x squared. When we have something that is a power of 4, look at what it is. it does that. And look at what happens when we have x to the 6th. The higher the power, the flatter the bottom half of the curve is. And it kind of looks like parabola. So this is x squared, then this is a little heavier, so x to the 4th, and then this is really, really flat, x to the 6th. So when you look at an x to the cube, it's a nice s, nice little flat shape here. But when we have x to the 5, this flatness portion gets a little wider. If we had x to the 7, we'd have an even wider flat surface for y is equal to x to the 7. And if we had, for an even power, x to the 8, we would have an even wider u for y is equal to x to the 8. So now we must talk about a thing called end behavior. End behavior refers to the following. What's happening near the ends of the curve as you go towards infinity? So what's happening with this? The y values get blown up. This one, the y values going up. And we also take a look at its end behavior on this side of the x-axis as we go towards negative infinity. So we actually need to understand how that works. So let's talk about end behavior. So for end behavior, we're saying that for x, for our x's that are ridiculously large, like billions, trillions, i.e. for going towards positive infinity or negative infinity, the group of the polynomial fx, so if you think of it this way, if I have fx is equal to an x to the n all the way down to a naught, then our function, fx, we say, tends to look like an x to the n, i.e. the largest power that you see. So let's quickly take an example. Let's say I have this function here. So let's say I have x to the y is equal to x to the 3. You know what? Let's make it even easier. Let's make it a little weirder. Let's say that I had y is equal to 0.5 x to the 3 plus 28 x squared plus 1. So then you would say as x goes to infinity, y tends to the leading exponent, that's the highest value, coefficient is our final answer. So it looks like 0.5 x to the 3. We'll continue talking about this at a later time. So now let's talk about how all this stuff works. So here's what you need to know. Let's say I have that function f of x is equal to, so let's say I have our function f of x is this. Now, here's what we say. For this scenario, if the leading coefficient an is bigger than 0, then our function tends to do that. But when, that's only if we're moving this way on the x-axis. And then if it's going in the negative direction on the x-axis, then our graph tends to blow up down towards negative infinity. Y is negative infinity. Now imagine if our an, the value that's sitting in front, is less than 0. So then what would happen is our graph changes again. Instead of blowing up, so in this case, as x moves to the right, our graph will tend to go down this way towards negative infinity. And similarly, if I travel along the x-axis here, our y's tend to blow up this way if our an is less than 0. So now let's talk about the rest of this. Now, these only happen because with this problem, the exponent is an odd number on the largest exponent. So that's what's happening there. Okay, so for an example of this would have been y is equal to x cubed. An example of this would have been y is equal to negative x cubed, where our graph literally does this, and this graph literally does that. And so now, what would happen if we had a even exponent for our graphs? So imagine if I had something like this. Y is equal to x to the 4. And then I had y is equal to x to the negative 4. Sorry, not negative 4, but negative x to the 4. Well, this is what our graph would look like. For the positive version, your graph would, as we moved along the x-axis this way, our graph would blow up that way. And then as we move towards positive infinity on the x-axis, our graph would blow up this way. So essentially, you're getting something that's kind of similar to a parabola. And the same can be said about this side of our equation. So as we go towards positive infinity here, our graph, instead of opening up, it's going to be going down towards y in a negative direction. So it's going to be flat, but then zips down so. And then as we move along the x-axis going towards negative infinity, the same can be said about this one. It does that. So in this instance, the y values get really, really negative in that regard. So now let's go on to talking about a thing called intercepts and multiplicity. So for x-intercepts, we're talking about some factor times some polynomial, and that x minus c factor that we have here will always be called a factor. And that's only if we know that f of the value c gives us 0. Okay? Then we know that the value c is a function of x. So that c is a 0 of the function f. That's all it is. So now if I have a function that has an x minus c raised to an m, then we say that this means that x minus c all raised to the m is still a factor. So now, what the heck does all this mean? I mean, seriously, let's take a look at it. So now let's go and talk about sketching this concept of x cubed minus 9x. We're going to do everything on this one page, and there's going to be four sections of work that we're going to do. We're going to test its end behavior. So let's do that now. So for y is equal to x cubed minus 9x squared, as x goes to plus or minus infinity, our equation, our overall function will look like y is equal to x cubed. And you remember our x cubed looks something like this. Okay, so that's what it's going to look like near the endpoints. Now, our graph may not look exactly like this, but you'll see that at the ends, we know that our graph kind of looks like that. Our ends are going to go off to infinity that way and then off to the infinity this way. So here's the reason why we had to study symmetry, and it's all about functions. Let's see. Start with our function f of negative x. And we substitute in. So we get negative x, and we're going to cube it, minus 9 of negative x. So cubing negative x cubed gives us negative x cubed. And then this turns into plus 9 of x. Now, here's the thing that we're trying to do. The moment you see this setup, you're saying, okay, can I pull out a negative sign? If I pull out a negative sign, it doesn't quite look like what we had before. But if we pull out a negative sign, it might. So let's try that. So we pull out a negative sign, and we end up with negative of x cubed minus 9x. And we know that this thing that's in the brackets is equal to f at x. So, therefore, f of negative x is equal to negative f at x. Now, we remember that we said that this means this is an odd function, which means that this is symmetric with respect to the origin. So what it means to be symmetric is if there's a shape around this side of my graph, then I'm going to have a mirror on this side of my graph. That's all it means. That's all. So now let's talk about the X-intercepts. When we're talking about the X-intercepts, we have to talk about that thing we said was called multiplicity. So we'll go over that, and then we'll take a full picture of what's going on, and then we will graph our function. So part 3 of our analysis makes us look at the intercepts of our graph. And when we're looking at the intercepts, we need to know what the Y-intercept is, and we need to know what the X-intercept is. So let's go and do that. So we have 0 cubed minus 9 times 0, which is y is equal to 0. So that means we have the point 0, 0 as one of our key points for our graph. Now I'm going to put a little box around that because we can use that later to help us graph. Now, let's go and calculate the X-intercept. So like we've been doing since grade 9, we're going to let y equal 0, okay? And when we let y equal 0, our equation becomes 0 I'm going to highlight this in blue so you can kind of see it. So we get 0 is equal to x cubed minus 9x. Now, the only way we can find the zeros here is we have to factor. So now when we factor, this is going to be x and then x squared minus 9. Now, equals 0. So we can also factor this part right here, because this is a perfect square. So now our equation becomes 0 is equal to x times x minus 3, x plus 3. So that means our zeros are going to be x is equal to 0, then 3, and negative 3. So those are our points. So now let's go and write our points down, and then we'll use them later. So we got 0, 0. We have 3, 0. And we have negative 3, 0 as our points. And I'm just going to highlight those in order for us to look at this later. So now we have all 3 points. Now there is an intersection point. All these points are 0, 0, negative 3, 0, 3, 0. Now, all we have to do is take a moment and graph that. So let's go and zoom out, and then we'll have a nice little graph of all the information that we have for this problem. Whoops. Whoa, it's all over the place. So there is our information. And then what we're going to do is we're going to go and sketch the graph. So we'll draw our graph. We have a couple of points. So we have negative 3 and positive 3. Negative 3 and positive 3, 0. So I'm just going to plot those points in red. We also have a center point, 0, 0. Now, all we need is some extra points. So maybe we could take a moment and make some extra points and then do this. So let me zoom back into my note, and we'll find some extra points for our calculations. So we take these extra points, we plug it into our original equation, and it was y is equal to it was x cubed minus 9x. So we'll pick a couple of points. So we'll take negative 1 and positive 1 because they are symmetrical about the origin. So it'll give us almost the same points. So when you punch in negative 1, you end up with 8, and then in the other one, you're going to get negative 8. For 2, you're going to get negative 10, and for negative 2, you're going to get positive 10. So now we have something nice to work with for our graph. So let's zoom out and see what we've got. So now we got all that information that will help us. So now let's go and plot those points. So one of the points is negative 1, 8. So maybe it's like somewhere up here. And then the other one is negative 1, positive 1, negative 8. So that's somewhere down here. When we have 2, when we're at negative 2, we're at positive 10. And then when we're at negative 2, we are at negative 10. And then all we have to do is we have to remember that from our original analysis, our graph is going to be kind of doing this, going off towards infinity. So so if we're coming from left to right, it's coming up this way, going up to this top point, zooming back down, going through these points, and then zooming back up towards infinity. And you always have to put an arrow. And that is our graph.
Mr. Simpson.
And that's it. So as a recap, when we started with this problem, we started with our equation. Then we had to test its end behavior. The end behavior told us what it would kind of look like in our problem. And it was really only showing you where our endpoints were. We didn't know what was going on the inside of our problem. So what we had to do was we had to, first of all, test our symmetry. So make sure that you say that you're going to test your symmetry. Then you test your endpoint, and then once you've got your symmetry, you have to find the X-intercepts and the Y-intercepts of the graph. Once you've got those, then all you need is a couple extra points to figure out where the graph is going to be drawn. And please take the time to try to draw this nice and smooth. Right, so I had an issue with my graph, so I just decided to graph it again with this blue little ink here. And now that I've got that, I'll draw my nice little red stuff. Now, you'll notice that it is symmetrical about the origin. So if you reflect it in the origin, all of the x's and y's flip around. So x becomes negative and y becomes negative if it just flips around. And you end up with something like this. Now, your homework. So just a quick recap of what we need to do. First thing that you have to do is you have to sketch your graph by figuring out the end behavior. 2, once you found the end behavior as x goes to plus or minus infinity, here's what you need to do. The next thing you have to do is you have to find f of negative x. Find out what that is. It's going to equal negative f at x, which is odd, or it's going to equal f at x, which means it's even. Now this one means, the first one means it is reflected in the origin. And this one means it's reflected in the y-axis. Now, this is the slightly harder part. You need to be able to calculate y-intercepts. That's why we studied that. So we need the y-intercept, and you also need the x-intercept. And what we need are the actual points so we can graph these things, right? So for the y-intercept, it's blank. It's 0 with a y value. And then this one, it's possibly several x's. So maybe x and then 0. Something like that. I need that from you. Then the last stage of this, you're gonna start by plotting the points that you know, see what you're looking at, and then grab some more points. And I tend to grab points in between the zeros. So just choose x's in between the zeros to see what your graph does. And you're done. So now on to your homework. Oh, and clearly I forgot to say, and you need to graph as well. Graph all those points. So you're going to be doing page 137, number 1 to 11 odd. And then you're going to do 13 to 18. Try them out. These ones are just extra practice. So if you get through the first 2 really easy, see if you can jump to some of the more difficult ones.